Welcome to the deep dive. Today we're tackling a real cosmic head-scratcher, one that's kept astronomers buzzing for years. The enigma of Tabby's star. You know, KIC 8462852. You sent over a fascinating stack of articles on this, and I gotta say, what jumps out immediately is just how completely weird this star's behavior is.
Oh, absolutely.
Yeah.
It really throws a wrench in our standard models of, how stars are supposed to act.
Totally.
And looking at the timeline, it really kicked off back in, early 2015?
Yeah, that's right.
You had this amazing group of amateur astronomers, the citizen scientists, digging through all that Kepler Space Telescope data.
Incredible effort, that Planet Hunters project.
It really was. And Kepler, its main job was hunting for exoplanets, right?
Yeah.
Looking for those little dips in brightness.
Exactly. Staring at hundreds of thousands of stars, waiting for a planet to cross in front.
And that's when they found it. This one star out in Cygnus, maybe 1,400 light years away, acting really strange. It was, blinking.
And blinking is putting it mildly, isn't it? This wasn't just subtle flickering.
Not at all.
We're talking massive drops in brightness, sometimes dimming by over 20%.
20%, that's huge. I mean, think about Jupiter passing in front of our sun. That's like, 1% dip? Tiny.
Right. So 20% is just off the scale for a planet.
And the pattern, or really the lack of a pattern, was just as baffling.
Completely erratic. Not regular like a planet's orbit.
Exactly. And then this is where it gets even weirder, like you pointed out from those historical records.
Yeah, the long-term dimming.
Right. Evidence suggesting this star has actually been slowly fading for, over a century.
Some studies suggesting maybe 20% dimmer since the late 1800s. And even Kepler saw it dip 3% in just 4 years.
Which is just bizarre for an F-type main sequence star like Tabby's. They're supposed to be stable.
It's like someone's got a dimmer switch on it, slowly turning it down, but also flicking it on and off randomly. It really paints a confusing picture.
No wonder it sparks so much speculation.
Huh.
You've got these sudden deep dips and this gradual fade.
So the big question, the one everyone was asking, was what on Earth, or, off Earth, could be causing this?
Right.
And let's be honest, some of the first ideas were pretty wild. The one that really hit the headlines.
Oh, yeah. The alien megastructure.
That definitely grabbed people's attention. The idea that maybe some advanced civilization was building something huge around the star.
It's an amazing thought, isn't it?
Yeah.
Catches the imagination. But, okay, let's maybe backtrack slightly. Kepler's mission, finding those planets, how did it actually work again? Transit photometry.
Yeah, exactly. Think of it like watching a distant streetlight. If a moth flies in front, the light dips just a tiny bit, right? Kepler did that, but for stars. It stared at a patch of sky, measured the brightness of tons of stars really precisely, looking for those small, regular dips.
Regular being the key word there.
Absolutely. A planet orbiting causes a predictable, repeating dip each time it passes in front, and Kepler found thousands of planets that way. Over 2,500 confirmed.
An incredible mission.
Yeah.
But it generated just mountains of data.
Way too much for the pros to sift through alone, which is where the citizen scientists came in, the planet hunters.
That's such a cool aspect of this story. People just volunteering their time looking at light curves.
Hundreds of thousands of them. And they were the ones who flagged KIC 8462852. They saw this light curve and knew it was something different.
Utterly unique. That huge up to 22% dip, like you said, compared to the usual tiny planet transits.
And just completely irregular. Random timings, random durations, sometimes lasting for days.
Out of what, 150,000 stars Kepler watched? Nothing else looked like this?
Nothing. It was a complete one-off. So strange that Dr. Boyajian herself, Tabby, who the star's named after, initially thought it had to be bad data.
You'd have to, right? Your first instinct is, okay, what went wrong with the instrument or the processing?
But they checked everything rigorously, and the signal was real. The star was behaving that strangely.
So the data's good. The star is weird. Okay, science time. What are the natural explanations? Where do you start?
Well, the obvious first guess, given Kepler, is a planet, maybe a really, really big one.
Right.
But, like we said, even Jupiter's transit causes a tiny dip, especially for a star bigger than our sun, like Tabby's star is, maybe 1% or less.
So to get 22%, you'd need something impossibly big, bigger than a planet.
Exactly. You get into brown dwarf territory, right? Around 13 times Jupiter's mass, deuterium fusion starts.
Yeah, a sort of failed star. But brown dwarfs have a telltale sign, don't they?
They do. They're warm enough to glow in the infrared. They give off heat.
And did they see that heat signature from Tabby's star?
Nope. Astronomers looked hard for that excess infrared radiation, the kind a brown dwarf would emit. Nothing there.
Okay, so no giant planet, no brown dwarf. Scratch that one off the list.
What's next? Dust. That's usually a good culprit for blocking starlight.
Right, especially in young solar systems. You get those big protoplanetary disks, loads of gas and dust left over from star formation.
And those disks can definitely block light, sometimes a lot of it. So maybe Tabby's star just had a really thick, clumpy disk.
That was the next idea. But the problem there is, Tabby's star isn't young.
Right, it's a mature star, F-type. Those protoplanetary disks, they mostly clear out pretty early on, don't they?
Yeah, the material either forms planets or gets blown away by the star's radiation and wind over millions of years. It shouldn't really have a massive disk like that anymore.
And there's that infrared problem again, too. Even an older dust disk would be warmed by the star.
And should radiate heat, infrared, which, again, they didn't really see in the expected amounts.
So no standard protoplanetary disk either. The plot thickens.
Okay, so if it's not a planet and not a normal dust disk, what else could cause irregular dimming? That led to the comet idea, right? The WTF paper.
Yeah, the swarm of comets hypothesis. The thinking was maybe a really, really enormous cloud of comets just happened to pass in front of the star from our perspective.
A huge, elongated stream of them. Individually tiny, but collectively. Maybe enough to block 20% of the light.
It sounded a bit out there even then, but it could, in theory, explain the irregular dimming, right? A clumpy swarm wouldn't block light evenly or predictably.
True. But the scale required, I mean, the sheer number of comets you'd need to block that much light was just astronomical. Pun intended, I guess.
Yeah, estimates were like hundreds of thousands, maybe millions of comets. The mass equivalent of several planets' worth of icy bodies.
Which just seems highly unlikely to exist in one place like that. Not based on what we know about solar systems.
And there was another big problem for the comet theory that came up later.
Ah, yes. The long-term dimming. We keep coming back to that.
Exactly. Those follow-up studies looking at historical data, plus the Kepler data itself, showed the star wasn't just having these short dips, it was also fading overall.
Over decades, maybe a century.
Right. And a passing swarm of comets just wouldn't explain that slow, steady fade. They'd cause temporary dips, sure, but not a century-long decline.
So the comet swarm idea, while creative, just didn't fit all the facts either.
So you rule out planets, you rule out standard dust disks, you rule out plausible comet swarms. What's left?
Well, this is where things got really interesting. And maybe a little sci-fi.
You mean aliens?
Chuckles slightly.
Yeah.
Well, yeah, like, astronomers are usually super cautious about invoking ET. And for good reason. History's full of mystery signals that turn out to be pulsars or something mundane.
Extraordinary claims require extraordinary evidence.
Precisely. But Tabby's star was just so profoundly weird. The observation so hard to explain naturally that the idea, well, it had to at least be considered. Maybe not likely, but possible.
And the specific idea that caught fire was Jason Wright's proposal, wasn't it? The alien megastructure.
Yeah. A Dyson sphere, or maybe more plausibly, a Dyson swarm. Some huge artificial construction built by a very advanced civilization.
The idea being to capture the star's energy.
Exactly. A Dyson sphere is this hypothetical shell completely enclosing a star. A swarm is maybe more realistic, a massive cloud of orbiting power collectors or habitat.
And if they were building it, or if the swarm was clumpy?
Parts of it could pass in front of the star, blocking the light in these irregular, significant ways. It kind of fit the weird light curve, at least superficially.
And the moment that idea hit the mainstream, media frenzy.
Oh, completely.
Yeah.
Alien megastructure found. Headlines everywhere. It was huge.
Even SETI, the search for extraterrestrial intelligence, got involved, didn't they? Pointed their telescopes at it.
They did. Used the Allen telescope array for, what, 2 weeks? Listening specifically for artificial radio signals, any broadcasts.
And the result?
Nothing. Silence. No signals that looked artificial.
Which, for many, kind of cooled the alien hypothesis.
It definitely dampened it. But, as some pointed out, does a civilization capable of building a Dyson swarm even use radio? Maybe they have technology far beyond our detection methods.
That's fair. Absence of evidence isn't evidence of absence, necessarily.
Right. So, the lack of radio didn't kill the idea entirely, but other evidence did start to pile up against the simple megastructure idea. That Kickstarter-funded study was key.
Ah, yes. That was brilliant. Raise money from the public to get continuous telescope time on Tabby's star for a whole year.
A global network of telescopes, watching it constantly. And they caught more dimming events in action, getting really detailed data.
And that data revealed something crucial about the color of the light during the dips, didn't it?
Exactly. That was the big finding published around 2018. Whatever was blocking the light wasn't blocking all colors equally.
It blocked blue light more than red light.
That's right. Shorter wavelengths, the bluer light, were dimmed significantly more than the longer, redder wavelengths during the same event.
And why is that such a big deal for the megastructure idea?
Because a solid object like a giant solar panel or piece of habitat should block all colors of light pretty much the same. It's just an opaque barrier.
It shouldn't act like a filter, preferentially blocking blue.
Exactly. But you know what does block blue light more than red light? Dust. Specifically, fine diffuse dust particles. They scatter shorter wavelengths, blue, more effectively than longer wavelengths, red. It's the same reason our sky is blue, actually scattering of sunlight by air molecules.
Ah, okay. So the color dependence strongly pointed away from solid objects and towards dust again.
Pretty much. Fine. Maybe cold dust particles that wouldn't radiate much excess infrared, explaining that observation too.
So if you have a big, clumpy, irregular cloud of this fine dust, that could maybe explain the short-term dips.
It could. And if maybe more of this dust is slowly accumulating in our line of sight over time.
That could explain the long-term dimming, too.
Potentially, yes. It started to look like the most plausible explanation based on the light itself. Dust seemed to fit the color data.
Okay, but we're back to the big question. Where did the dust come from? If it's not a young star's disk.
Exactly. That's the million-dollar question that's still not fully settled. If it's dust, what's the source?
There's that kidnapped moon idea from 2019. That sounded pretty wild.
It did. The scenario is basically maybe a planet got too close to Tabby's star, got tidally disrupted, ripped apart.
Okay.
And maybe one of its moons survived, but got thrown into a really close orbit around the star.
And in that close orbit, it's getting blasted by the star's heat and radiation.
And it's essentially evaporating or disintegrating, shedding huge amounts of dust.
Right. So the dust clouds causing the dips are coming off this dying moon.
That's the idea. And it could potentially explain both the short dips, clumps of debris, and the long-term dimming, a more general haze building up.
Yeah.
Some even suggest that the star might have briefly brightened when it ate the original planet before the moon dust dimming started.
It ties things together quite neatly, doesn't it?
It does try to, but again, challenges. That infrared signature problem, shouldn't shredding a planet and consuming it produce a lot of heat, a big infrared flare?
You'd think so. And they haven't really seen definitive evidence of that, have they? Some subtle variations maybe, but not a smoking gun? Not really. And there's the statistical argument too. Are we just incredibly lucky to be watching right when this super rare planet shredding, moon evaporating event is happening?
Seems a bit coincidental for the only star out of 150,000 showing this weirdness.
Right. It feels a little convenient. Possible, maybe, but maybe not the most probable explanation.
So, if not dust from a destroyed moon, what other dust source is plausible?
Well, the other main contender is simpler, in a way. Interstellar dust.
Just a random cloud of dust floating between us and the star. Nothing to do with the star itself.
Exactly, just a patch of the interstellar medium that happens to be denser or clumpier along our line of sight to Tabby's star.
How would that explain things?
Well, if the cloud has varying density, denser bits drifting in front could cause the deep, irregular dips. And if the whole cloud is slowly moving across our view, or we're moving into a denser part, maybe that explains the long-term dimming.
And it doesn't require any crazy rare events happening to the star.
Right. It avoids the need for exploding planets or evaporating moons. But there's always a but, isn't there?
Seems so with this star. The but here is, well, two things. First, if it's an interstellar cloud, why only Tabby's star? Surely a big cloud would dim other nearby stars, too.
Good point. And they haven't seen that.
Not clearly.
Yeah.
No. And second, there are now hints, maybe, of a cycle in the dimming. Roughly every 4 years or so, some analysis suggests.
A 4-year cycle. How would that fit with a random interstellar cloud just drifting by?
It wouldn't, really. A cycle suggests something related to the star system itself, something orbital, maybe, not an unrelated cloud. So that emerging pattern, if real, argues against the simple interstellar dust idea.
And this star just refuses to be simple, doesn't it?
It really does. Every time you think you have a neat answer, some new data complicates it.
So wrapping this all up then, after all these years, all these studies, where do we actually stand? What's the consensus, if there is one?
I think the broad consensus is that dust is almost certainly involved. The way the light dims differently at different colors is just too strong evidence to ignore.
Okay, so dust is the culprit.
It seems like the most likely physical mechanism causing the dimming, yes. But where that dust is and why it's there, that's still very much up for debate.
So the origin is the mystery now. Is it circumstellar gust from some weird process, or is it interstellar? Or something else entirely?
Precisely. The what seems to be dust, but the why and where are still open questions.
And the alien megastructure idea, is that totally off the table now?
The simple solid megastructure blocking light like a screen. Yes, the color data makes that very, very unlikely. But, could there be some super advanced technology interacting with dust, maybe manipulating it in some way?
Ah, like nanoscale structures or something even more exotic.
It's highly speculative, of course, and Occam's razor usually points towards a natural explanation, even if we don't fully grasp it yet. But you can't entirely rule out something technological, just it's become a much less favored hypothesis compared to some kind of natural dust phenomena.
So the bottom line is, aliens are probably out, dust is probably in, but we still don't know exactly what kind of dust situation we're looking at.
That's a pretty good summary, yeah. The excitement of the alien megastructure phase has largely passed in the scientific community, replaced by the perhaps less glamorous but equally challenging puzzle of figuring out the precise nature and origin of this unusual dust. It's still a major astronomical mystery.
It really is, and this whole saga, this deep dive into just one weird star, it just highlights how much we don't know about the universe, doesn't it?
Absolutely. We build these incredible instruments, gather amazing data, enlist help from people all over the world, and still, the cosmos can throw us these curveballs that completely defy easy explanation.
It makes you wonder what else is hiding in that Kepler data, or data from TESS or future missions. What other weird light curves are out there waiting to be found?
Exactly. Tabby's star is a fantastic reminder that there are still genuine mysteries out there, phenomena that push our understanding and force us to think more creatively about astrophysics.
A reminder that the universe is still full of surprises. Even when we think we've got a handle on things, something like this comes along and shows us there's always more to learn.